Now we will solve the problem 5.13 of Griffith 4th edition Electrodynamics. The problem 5.13 is very simple, uh, so we can solve quickly. Suppose you have two infinite straight line charges of lambda, a distance t apart, moving along at a constant speed v as shown in this figure. How great would we have to be in order for magnetic attraction to balance the electrical repulsion? Work out the actual number. Is it is this a reasonable sort of speed? So we have to find this one. Now you take two infinite line, straight line in which carries the charge per unit length lambda. Both are in same direction. That is, it is parallel current. We know very well parallel current repels each other. However, this magnetic field, using a right hand rule, you can see verify easily this magnetic force is attracting one. So, magnetic field due to both the current will attract each other. So, with that understanding, we will move on to the following. That is, magnetic force per unit length is equal to mu naught divided by 4 pi I into I, because this current is I, here also I, divided by the distance t. Now you know that this is magnetic force per unit length, because we are dealing with a charge per unit length. So now I can be written as I is equal to the lambda multiplied by V. Lambda is a unit charge per unit length. If you multiply this by V, you will get the current. So here both are equal charge. So naturally, this will be I into I squared. That is lambda squared V squared over T. So the magnetic force of attraction is equal to mu naught over 4 pi lambda squared V squared over T. Now we will come to the electric force. Electric force is actually this is a repulsive one, because light charge repulse each other. Then F of E is equal to 1 over 4 pi epsilon naught Q into Q divided by T. So the charge, this is electric force per unit length. Like here we have seen the magnetic field per unit length. Here we are going to see the electric field per unit length, which is equal to lambda into lambda. So this will become lambda squared divided by T. Of course, you have 1 over 4 by epsilon naught lambda squared over T. Now you equate both, that is this one, mu naught over 4 pi lambda squared V squared by T, and this 1 over 4 pi epsilon naught lambda squared over T, because we have to balance both the electric force and magnetic force. Now, interestingly, this 4 pi will get cancelled. Similarly, this lambda squared will get cancelled, and also this T will get cancelled. So in the left hand side, you will have only mu naught this V square. In the right hand side, you have only 1 over epsilon naught. So if you bring mu naught to the right hand side, then V squared will be mu naught epsilon naught. So naturally V, if you take square root, this will become 1 over square root of epsilon naught mu naught. We know very well that 1 over square root of epsilon naught V naught is equal to the velocity of light. Yeah, we need not do any substitution. Even if you substitute, you will get the velocity of light. That is 3 into 10 power 8 meter per second. So here you can see this is actually highly impossible, because this current charge has to move with the speed of light, which is uh, highly impossible. So naturally, what it means, we cannot obtain the velocity of light. So this magnetic force will be always lesser than the electric force. So the electric force, in other words, we can say this electric force always dominant than the magnetic force. Thank you very much for watching my video and supporting me continuously. Thank you very much.